Good morning, calculus students. Calculus students are in the house. April shows up face to face. Is that your cat? What's your cat's name, April?
This is my dog,
Dog. What's his name? Her name?
Omi.
Only. Outstanding.
I don't know why she's on my shoulder today.
That's cat-like. That's cat-like behavior. Climb up on you for some petting. Nothing wrong with that. Probably make you do better in calculus. All right. It is Monday. Let's get this show on the road. Oh, that's right. I'm probably going to get this iPad hooked into this.
Real quick, I have a question.
Please.
So I noticed we have a quiz due on Wednesday, and usually after quizzes we have tests. So do we have any tests coming up anytime soon?
No, it's just that chapter 6 is pretty long. So that's the only thing going on there.
Okay.
Yeah, good question. Let's see. I'm in a new location today. Just a second. I got to get the password. Join. Forgot about sharing my screen. See if we can get this figured out. Forgot about getting my iPad on the network too, so sorry about that. Marvelous. Well, good morning, everyone. Welcome to Calculus. I am coming to you this day from, let me try to get that ridiculous glow gone. Coming at you from the glories of Santa Cruz, California. Came down here this weekend to mountain bike with a bunch of other old guys and had a good time, but now I got a big gash out of my leg from crashing, and I won the most crashes award for the weekend, so but my brain is engaged and there's nothing I can't do with calculus. So let's see, we will talk after class. I'll try to get us done quick enough that you can ask some questions about anything else you want to ask about. I had a few questions about things that went on in the homework. One of the questions in the homework that was just kind of tricky that I don't know if you survived was the e to the say 5t plus c questions. Unfortunately, e to the 5t when t is 0, e to the 0 is not 0. So figuring out what that constant is for the initial time was kind of tricky. So that caused some people some problems. And anyway, So today we in 6.3, where we will start to find actually volumes, which seems strange. How are we going to find volumes? And so to start with, I brought a parabola in, and so I gave you kind of 3 constraints for an area. So in the previous section, you would have said something like, hey, what's the area of that shape over there? And again, I hope that's not a hard question to you now. I hope that you look at that and think that's really cool that we can find the area of something curved now, as long as there's an equation that identifies it. Notice this particular one, it takes 3 equations. Y equals 9, the horizontal green line, x equals 2, the vertical blue line, and the red parabola. It takes all 3 of those to enclose a space. So that's what changed in the last section. But now what we're going to do with that same exact area is a couple of things. One, we're going to spin it around axes, causing it to develop a 3-dimensional shape. And this is such a neat idea, and it's something I want you to get. So I carved out 2 days in the schedule so we can discuss it a lot. And then there's a little bit more contrived questions in your assignment. I want to start with those just so that it, I don't know, makes the most sense to you. So we're going to take that area, but this time what we're going to do with it is use it to make a volume. And there's some kind of, this is very contrived in my opinion. I don't really like these questions so much, but there's 3 or 4 of them in your assignment, and I want you to understand the logic. And so let's do the first one like this. Like, what are we going to do with that area enclosed by those 3 equations? Well, let's do this. Let's do something, I don't know if I want to say, I guess I'll say easy. But what if that area was, or that volume was created by filling it with squares? What do I mean by that? So what we're talking about here is a flat surface, but now instead of that being flat, we're going to imagine squares stacked on top of them. And do you notice that those squares could be either parallel to the x-axis, and I'll try to sort of pretend this is sticking up in the air toward us in 3 dimensions. Squares sticking up toward us like this. And of course, those squares would have a little thickness to them, and as they move down in this direction, they would get smaller and smaller and smaller. But do you notice that's not the only way the squares could go? They could also go parallel to the y-axis. Does that concept make sense? They could go parallel to the y-axis as well. So the questions that you're reading will kind of word that. You can't just say, hey, there's an area and let's just pretend it's full of squares, because you got to think about which direction are they going to go. So in this case, you would either say, oh, those squares are parallel to the x-axis, or you could say, well, they're perpendicular to the y-axis. And of course, it really helps to kind of draw a picture like this. You certainly want to get your graphing calculator out at very least and sketch out the graphs and kind of get your idea around what that space entails. And then maybe try to sketch these in place. Of course, Desmos is even better, but the problem is you're gonna, it's gonna be 3D, and so you're not gonna be able to graph these in the ways that you've done in the past. So let's say filling with squares, and we'll say parallel to the x-axis. So filling it with those squares, ultimately those are, because they have to have a thickness to them, since we're going to find a volume, they're really not squares, they're really prisms. But because the word square is used, whatever this length here is for x, since it's in the x direction, then this height is also x. So we're kind of being told that those are identical. So down here, that distance is going to be smaller, of course, as we kind of move down the shape. But my question to you is, what are you going to call this part of the, and this is important that you be able to do this, what are you going to call that part of the rectangular prism or that rectangle. What are you going to name that? Somebody make a guess at what we would call that.
D for depth.
Yes, and specifically D because it's tiny, but maybe even better, D what? That's a little bit of what, I guess, is the question that I'm fishing for. And I am asking you to read my mind. So of course that's not going to be easy to do. But there's something we want to call this that's pretty important to call it, to name it correctly.
Because we're filling this with infinite squares per se, like we did with triangles, is it dx for like kind of the width? I think you know what I mean, but like the width in this case is the depth.
You're exactly going the right direction. But because those are sort of vertical, does it make sense they're along the y-axis? And so we wouldn't call them dx, we'd call them dy. Does that make sense? Because they're sort of vertical. Maybe that's kind of tricky. So the point is, as we cruise along, those x values are going to change as you move kind of down the shape. And do you notice that this is going from, well, either this shape lives from y equals 3 to y equals 9. Or it lives from x equals 2 to x equals 4. Do you see how that is not obvious? Like which ones we're doing here?
Aren't we doing the 2 to 4 because based on your drawing, it's going up and down, right?
Yeah, and at this point, that's actually kind of not determined. And so, Connor's hypothesizing, aren't we doing it from 2 to 4? They're both true. Like we're doing it from x is 2 to 4, and we're doing it from y is 9 to 3. The question is, are we going to do this with x's or are we going to do it with y's? That's kind of the question. And what really determines that, one of the things that makes this stuff hard, is you're sort of stuck. You're stuck with this. You're stuck with dy. In other words, it's hard to switch out dy. And so it's kind of better to do this with y's. That's kind of the idea here. Now, I guess
so if this, sorry.
No.
So if the squares were the other direction then and we were stuck with dx instead of dy, would we solve it in terms of x?
Yeah, and we might do that. Like we might do both just to kind of help you see how this works. So the squares are going this way. And so would you agree with me that these lengths right here are x's? I mean, this is an x of 2 to an x of 4. Notice we know this distance is perfectly 2. But then when you get down here, you certainly start with an x of 2, but now x is much shorter. And so this length right here is in the x direction. So these lengths are in the x direction. So we're sort of stuck with that this time. And so you have this mixture of x's and y's every time you do these problems. So let's just see what that would look like. Well, again, what are we really doing in calculus? Well, we're adding up all of those volumes. So the key is, how do you write down the volume? Well, because that shape is a rectangular prism, a mathematician would call it, a box is what any normal person would call it. The fact that I have it labeled is kind of the key. Does it make sense? It's really x times dy. In other words, that's the volume of a box, is length times width times height. So because they told us they were squares, thank God they told us that, because we would never have known how tall this was. Now they could have done something tricky, and thank God your assignment isn't stupid enough to do that. They could have said the height here, the height of it is double the length of this. And so we could have said that's 2x. And I mean, you could do all kinds of creative things, but in this case, they're told we're filling it with squares. So that means length is the same as the height. So since this was called x, I was able to call that x, even though it's kind of coming off the page toward us. So my question is, does it make sense based on the labels that we have that I would say the volume of this is x times dy? And I'm just going to add those all up.
I feel like this is wrong
In what respect?
because the boxes get smaller. So wouldn't you need to include that red parabola somehow?
That's
Because
exactly-
that determines how smaller they get.
Yes, and you're exactly right. So that's bothering you, Eve, that it's bothering you when you look back at the graph that it's like, well, X up here is, you know, big and down here it's really small. And so how can you just say it's X? Well, that's kind of the beauty of this. When I drew a red star kind of around dy and said, hey, you're stuck with y's. In other words, down here, I can't do this problem. If I just gave you that right there, and I didn't even give you any context, but I said, hey, find the answer to that question right there, you'd have to say, I can't do it because I can't take the integral of x's with respect to y. Like that's x's and y's. You can't do that. So somehow I've got to get rid of the x's. Well, do we have some way, kind of like substitution, do we have some way of switching out x's and y's? And that's the answer to your question, Eve, because this equation right here tells us how x's and y's are connected, and that is the parabola. Then that's how the parabola is going to get involved, so that x kind of isn't the same thing every single time. So let's think about this. So we're stuck with y's. So we knew that y equals 1/2 x squared plus 1. Was that it? We knew that y equals 1/2 x squared plus 1. So if I subtract 1, multiply by 2, so I have 2y minus 2 equals x squared. So that means x equals the square root of 2y minus 2. You agree with that? So those two are two equations that say exactly the same thing. So this is how I do it. In other words, I'm going to replace this statement right here with what's sitting in there. And notice I get really lucky because I was thinking to myself, uh-oh, I've got to take the integral of a square root. That's going to be ugly. But notice in this case, it's getting squared. So that means I actually get to get rid of it. So that means this becomes square root of 2y minus 2 squared. So that just means 2y minus 2. What's missing now? I'm almost ready. It's like, hey, cool, y's. Right, I can take that integral. What's missing now that's important?
Your limits?
Yeah, notice now we have the answer to our question. Where does this shape live? Is it from 2 to 4? Or is it from 9 to 3? Well, because we now realize we're stuck with y's, since one of our dimensions was dy, then we're saying, okay, well, then I'm going from y is 3 to y is 9. And so I'm going to write that in here, y equals 9 to y equals 3. Again, you don't need to write y there, but it's just kind of important to know, hey, those are y's. So everything is in terms of y. So what makes this section hard is you can take this integral, but in this section, you got to write that integral for yourself. And it's kind of cool because this is the only time you'll ever use this. Again, I'm always kind of harping on the fact that I like this stuff for practical reasons. And no one's ever going to give you some integral and say, can you take this integral? Like if you're ever going to use it, it's going to be like, well, the project where you're going to have to create the integral yourself. So what this equation is going to do is take care of the fact that our y value, well, really our x value, is going to get smaller and smaller and smaller as you move down. So let's see what this results in. So you should say, yeah, that's a pretty easy integral to take. So the integral of 2y is y squared. The integral of 2 is 2y. I can evaluate that at 9 and evaluate that at 3. Seeking calculator in bag. Found 81 minus 18. 81 minus 18 is 63. So I get 63, and then 9 minus 6 is 3. So I end up with an exact answer of 60. So that's actually a volume. Again, I'm going to write cubic centimeters. There was nothing in this problem that was saying those boxes on the graph were in centimeters, but I just hate writing cubic units because it just doesn't speak to me very well, and I'm afraid it doesn't speak to students. And so if I go over here and say, hey, that's centimeters and this is centimeters, I can, I guess, arbitrarily do that if I wanted to. So, I wonder if I would get the same answer if we did it the other way. Copy. Let's see, how do I get you to paste? I don't know. Guess I'll have to do it again. I'm going to give you a second to kind of see if you can do this the other direction yourself and see if see how that works. Just give you a second to think about it. Let me draw a picture of it first, just so you have a feel. So the question is, what if we said example 2, where the squares are not parallel to the x-axis, but perpendicular to the x-axis? So what we're saying this time is our squares look something like this. So we have long, thin squares, but they're coming toward us. So they are squares. So this is a Y and this is a Y. That's what those heights are. And then they're sticking up off the page toward us. Maybe something like this. Again, that's a bit of an optical illusion. To me, for some reason, those look like they're going down into the paper, like below the graph for some reason. So the fact that they are squares means this height here is also Y. If this distance is Y, then this distance is also Y. How thick are they? How thick is this? That distance right there, how thick is that? Notice which direction it's going.
dx.
Yeah, it's down here in the x direction. So that's a little bit of x. So the question is, can you write out the integral? Can you write out the integral that would allow you to add up all of those rectangles? Those squares that have a thickness of dx. Can you write the integral out for that? Did you get this? The volume of that particular shape is no different than it was before. Length times width times height. In this case, though, I've got length times width, y times y times height. Sort of doesn't matter which one is which. I don't know which one to call length, width, and height, but it's the 3 dimensions of it are y, and a little bit of x. Notice it's exactly the same equation we had a second ago. except for everything is switched. Instead of x times dy, it's y times dx. Do you see that in the picture? It's very important you see this. Don't just write it down. Like, you got to visualize it. Slow down and ask questions. Ask me to re-explain things. As I said before, you're a little bit stuck with dx. In other words, it's harder to change the dx into dy. Having said that, could you do it? This is something that did not occur to me till later on. Couldn't you take the derivative of that according to substitution? Couldn't you take the derivative of y equals 1/2 x squared plus 1 and get an equation that had dx's and dy's in it? You could actually switch that dx out. But it's easier to switch the y out. Do you agree with that? So since I know that y equals 1/2 x squared plus 1, then couldn't I just take that statement right there and replace y with it? Now it's all x's?
No, because that's for y. You have y squared.
Yo, I'm replacing y with it, but I'm going to have to square it. You're right, Eve. In other words, I'm replacing y, but I'm going to have to square it. In other words, this now says 1/2 x squared plus 1, but it's still squared. Is that what you're getting at, Eve?
Yeah, I thought you meant just replace y squared like you did with x.
Good job. No. And then what am I missing? What else has got to go in this? Notice, because I'm working in x's, where does this stack of boxes live?
From
2 to 4?
Yeah, 2 to 4. And again, you don't need to write this, but it's kind of a good practice to get into, maybe, especially in this section where it gets a little confusing. Just remind yourself, hey, these are x's. So now I have an integral, and so I can kind of forget about the picture and just answer the question. Do you think I'm going to get the same answer I got before? What do you think? You think that'll be the same volume? I'm guessing.
Shouldn't it be?
I'm guessing
It's
no,
the
but
same.
because think about how tall, like this one, I'm not sure, but like this one is really long, which means it's going to be really tall. Does that make sense? It seems like that's going to be a really large slice right there. So I'm not sure. I'm not sure. I wish I had a way to kind of actually draw this 3D shaded for you so it looked a little bit better. Let's see. Well, I think the easiest way would be actually to square this out. In other words, that integral is junk squared. So I'd have to, if I wanted to, I can't do it right now. Like, I could let u be equal to 1/2 x squared plus 1, but I'm thinking, well, why don't I just square it out? Then there is not a function inside of a function. So if I take 1/2 x squared, that'd be 1/4 x to the 4th. And when you FOIL something out, I hope this is easy to you as a shortcut, but the middle one will be these two multiplied times 2. So 1/2 x squared times 1 is 1/2 x squared times 2. That'd be x squared. So I think this is x squared, and then 1 times 1. I think that's what I get if I square this out. And so now I don't have a function inside of a function, and then it's just power rule. See how it made my life easier? I didn't have to substitute. I didn't have to change x into some other letter. Maybe I could have done that. But in this case, I just rewrote it. And nothing else changes. So if I take the integral of 1/4 x to the 4th, the x to the 4th grows 1, so it becomes x to the 5th. I divide by 5, so now I get 1/20th x to the 5th. The x squared grows an x cubed, and then you divide by 3, and the 1 grows an x. And I evaluate that at 4 and 2, and I should have my answer. So again, I didn't pre-prepare this to just write it down, but I'm glad of that because it gives you a second to process. So I'm sticking in 4 cubed divided by 3 plus 4. I got 76 0.53. And I'm writing this off. Let's see. Well, I'll go ahead and write it exactly. I didn't convert this to a fraction. Maybe I should. Yeah, maybe I will. If the book asked me for an exact answer, I could just go back in and go math and say convert this to a fraction, and I got 1148/15. Let's change colors. Now I go back in and reevaluate this as a 2. Where did you go? Terrific. I get to type it all over again. 2 raised to the 5th divided by 20 plus 2 to the 3rd is 8 divided by 3 plus 2. I got, converting to a fraction, I got 94/15. So it's kind of cool. It's not really surprising that I got an exact an equal common denominator. So if I subtract those two, I got 1,054. Little side note, anybody know how to tell if that number is divisible by 15? Anybody know the cool shortcut? I'm just going to type it in my calculator and maybe I'll get lucky, but does anybody know how to tell if it's divisible by 15?
You add up the numerator to see if it's something that is divisible by the denominator.
That doesn't always work. It works for 3 only. So in this case, because 15 is made of 5s and 3s, the 3 trick has to work. In other words, 5 plus 4 plus 1 is 10. That doesn't divide by 3. So the 1,054 is not going to divide by 15. And then because 15 is made of 5, then that means 1,054 would have to end in a 5 or a 0. So this is not going to divide. So I'm done. It doesn't divide by 5 or 3. So I can actually already know this is reduced and I'm done. Who cares? But that's just kind of cool to know.
Is it good practice to be giving exact answers?
Yeah, but I could care less on a test. Obviously, you can go all the way back to here on a test and just type that in your calculator. So I'm going to want to see you work it out. I mean, it's a part of this class. But if I see this work right here and then you give me an approximate answer, I'm not going to say on a test because I don't care. I like this stuff for the real world and nobody wants that for an answer. Does that make sense? I divided it and got a little over 70. So saying approximately 70 cubic centimeters or whatever is like nobody knows what to do with 1,054/15. So I'm in the minority of math teachers, but I would almost prefer decimals myself. But again, that's actually personal. If you're a person that it sort of defeats the purpose to do all this math and then give an approximate answer. So I understand why mathematicians say that. But again, it's just important to kind of point out that what you just found is not just a number, it's a volume. We're finding volumes.
Wait, why is this not the same as the other squares? Because it's the same shape.
Yeah.
So I feel like you should find the same volume.
At the risk of, actually I can use this figure. At the risk of, I think I'll erase this, but at the risk of totally screwing this up, I'm going to try to draw this out a little bit. So this length is the same as this length. So I'm going to try to draw this first square in here. And then it actually kind of works its way down to here in both cases. Would you agree that's kind of what this volume? Yeah, that was a bad decision. That made it worse. It's very hard to draw 3D in 2 dimensions. Can you picture that that's what that shape would look like, the first one? It's better than it was before. So it's kind of, its largest square is, well, isn't this 2? So its largest square is 2 by 2. And then it just gets smaller and smaller and smaller down to nothing. Do you agree with that? So then the one we just did, what would that look like? Well, that would be, well, over here. So this first square is from here to here. And oh boy, is this even a smart thing to try? This height is exactly the same. So there's the first one. Man, I'm having a hard time picturing that. And then it works its way all the way to nothing. Is this right? I think that's right. That probably doesn't help. You're probably just looking at it going, hey, a bunch of squiggly lines. Very hard to picture, isn't it? So actually, I mean, if you draw it a little bit, that first square, because this goes from 9 down to 3, this is a 6 by 6 square. So that first one is a 6 by 6 square, and then they just get smaller and smaller and smaller. Notice this one goes from here to here. Whew, those are hard to draw. So actually, it does, I think, make sense that they're not the same volume. They live in the same space, but they're being used for kind of different purposes. So I don't think they would be. So what do we get? We got 72 for that one, and we got exactly, what was it, 60? Yeah, 60. We got 60 for this one. So they're not way different, but they're not the same. And I don't think they're going to be. So that's just interesting.
It seems like, looking at it from a practical standpoint, if you told somebody you need 60, feet cubed of lumber to fill this space, and they decide to cut it long ways instead of x-axis like you told them, they're going to come out with the wrong amount of lumber.
Mm-hmm.
So it's actually important whether you go parallel to the x-axis or parallel to the y-axis.
Yeah. Now, if this sort of triangular shape that we're talking about here, I say triangular because this is curved, so it's not really a triangle. Now, if that came out toward us and it stayed the same size, in other words, a prism, it didn't get smaller and smaller and smaller, it just stayed the same triangle as it went up, then it wouldn't matter what way we sliced it. But in this case, because it's kind of pinching to 0, it does make a difference. Let me ask you even a third question about this. What if we took that same exact area, but what if this time we actually made semicircles out of it? What if we filled it with semicircles? And again, we're thinking of those as having a thickness to them. I'll try to draw them with a slight amount of thickness to them. Could you set up that volume? One of the things I like about this question is it's starting to look like an airplane wing. It wouldn't be a semicircle if it was an airplane wing, but maybe an ellipse if we made it really hard. But can you picture this as being a little bit like an airplane wing? All of a sudden it sort of feels like, hey, this is actually something now. But this time the volume is not length times width times height. You've got to see this as a circle that's been chopped in half. So you know the volume of a cylinder, yeah? Volume of a cylinder is the area of the circle, pi times radius squared times the height of it. It's a stack of circles, that's what a cylinder is. So this time the formula for the shape we're talking about is not a stack of boxes, it's a stack of cylinders, well, half cylinders. So this would be semicircles. I guess I could say parallel to the x-axis or perpendicular to the y-axis. Write something out, even if it's wrong. If you're having trouble picturing this, I'm going to redraw the middle one. Actually, I'm not going to redraw it. I'm just going to draw a new one. What you're really doing is you're taking a slice you're taking I tried to draw it 3D before just to help you visualize it, but really if you looked at it from above, it's just a slice like that. I'm slicing here and I'm slicing here. It's just that the top of it is actually kind of got the curve in it, if you will. So literally from the top, you wouldn't be able to see the curve. Does that make sense?
So,
This
can
is
you hear
hard, by
me?
the way. Go ahead, Cheyenne.
Is the curve, that's the part that's coming out towards us?
It's coming up. Like if you're looking down from above, the curve is coming towards your face.
Okay.
And you have a question in your assignment. These questions are harder, I think, than the ones we're going to get to in a minute because it's hard to visualize. Hardest part of this, I think, is picturing it. Do you see this is kind of looking like the top half of a carrot? You slice the carrot kind of down the middle. So what's hard about this? Well, let's take a look at that slice. Would you agree that because that slice is in this direction, that's a little bit of why? And because the formula for a cylinder is asking for two things, the height, which we just figured out is a little bit of y, and that might bother you because the height is laying down. But if you had a cylinder that was laying here like this, the height is that distance. Doesn't matter which direction that thing is laying. But the other thing it's asking for is the radius. That's not good. Why is that not good? Well, isn't the radius that distance right there? Isn't that the radius? Anybody have any brilliant ideas? How am I supposed to figure out what the heck that is or what to call it? Like part of me wants to say, okay, great, I got it. It's the integral is pi times radius squared times height. You're not wrong if you say that. But just like last time, it's not good that there's an r there. That's even worse than an x or a y. Because if you will, I'm stuck with dy.
Isn't it?
Yeah, go ahead. Take a stab.
So isn't the diameter the x length? So wouldn't the radius be half of the x length?
That's exactly right. Isn't this distance right here, all we have to do is cut that distance in half, don't we? If this is our slice, if that's our slice right there, don't we have to just take that x and cut it in half and that'd be our radius? So x divided by 2 would be the radius. Notice it's still squared. But notice that's particularly tricky because to get what that x is, looking at the screen, I've got to go all the way to here, which is kind of like x1. And then I've got to go all the way to here, which fortunately that's a constant, that's 2. So does it make sense? That x that we're talking about right here is really equal to x1 minus 2. In other words, the parabola minus 2. Is this hurting your brain? Should. This is kind of where brains begin to hurt. In other words, what I'm getting at is you might have came back here and said, okay, great, we're going to work with y's. And so since y went from 9 to 3, then I'm just going to come in here and say y equals 9 to y equals 3. And then all I have to do is replace that x, as we said earlier, x was equal to, I forgot what we said earlier, I'm going to go find it. That was at the very start. We said that x was equal to the square root of 2y minus 2. Like there's a part of me or a part of you that might have thought, that's all I have to do. This is great. I'm in good shape. But does it make sense that would have made the x distance all the way to here? In other words, that would have caused our slices to go clear to the x-axis. And by the way, I'm a little worried that we didn't screw that up in the previous problem now when I think about it that way. Was that wrong before? Maybe I don't know. Let's go back and maybe we'll go back and think about that later.
Should that be over 2 since we're doing half cylinders?
Yeah, I was actually just wondering about that too.
Yeah, that's right. We aren't doing complete cylinders, are we? So we forgot the divided by 2, we being me. So it's really pi r squared divided by 2. Good catch, because it's a half cylinder, isn't it? It was a semicircle, not a complete circle. Thank you. Good catch. So let's see then, what does this really look like? From 9 to 3, I've got a pi and a divided by 2, which I could pull out front, and I probably will pull out front. So I've really got the x value of the parabola, minus, I'll switch colors, the x value of the line. This is what I was saying back here earlier. To get just that x right there, I've got the x value of the parabola minus the x value of the line. And that is what I am dividing by 2 to make a radius and then squaring. The question is, can you agree with that?
So that square root expression, that's the x value of the parabola, right?
That's exactly right. So then if I pull this pi over 2 out front, leaving 9 and 3 here, the x value of the parabola was 2 the square root of 2y minus 2. Maybe I'll switch colors just to keep your brain as clear as possible. And the x value of, what's the x value of the line, since that line was vertical? It's just always 2. Thank God that's so simple. It's not an equation. It's just 2. There.
So Doug, isn't there another 2? Like, I'm just getting kind of lost in all the
Yeah.
2s because like we have, because I was thinking the x parabola is square root 2y minus 2. And if you look at the x or the second equation down that's still written in black, it looks like you would have x over 2 squared over 2 again because we're doing half circles. And then we add another 2 on top of that for the line. Isn't like, I just overthinking this?
I'm not sure. I got to think about that with you. In other words, I think Cheyenne pointed out, hey, what's a half cylinder? So it's supposed to be a divided by 2 there. So I think that 2 is right here. So I didn't.
Yeah, but where does it land on the?
So I think we're okay. Now, keep in mind, like this question is inordinately painful. I don't think we missed anything. So this divided by 2, and the fact that I wrote, and I'll go ahead and kind of mark this out here, but this x right here, what I called x right there, that's this x right there. In other words, I'm just recognizing it. Hey, that x is found by subtracting a couple of things. That x is found by the parabola x minus 2, if you will. So that's why we went back and said parabola's x minus the 2. So there's the parabola x, but switched into y, and then minus 2.
And then the 2. Okay, that does make sense. Sorry about that.
You should not be sorry. We need time to process. Now, I will tell you, like, this is not a very good example. This is because I'm sort of purposely making these up by scratch. The hard part is like, how do you conceptualize the integral? I'm not even going to finish this. We're done. Like I could cheat on my calculator to answer this. That's the second problem. And that particular one looks hard. I actually think this integral that I just wrote right here is an example of something that I really should put on a test, and won't be in your homework because this is a hard integral. So you got to be a little careful.
Well, can't you just, I mean, doesn't that square root go away if you were to do the, if you were to multiply it out? with the squared.
Yes, it's going to go away when you square this, but the problem is then you have to take 2 times this. Remember, you have to FOIL it out.
Oh, yeah. Okay.
So, and I'm not saying this is impossible. It's not impossible at all. You can definitely do this integral, but you do need to multiply it out. And I would say, just to write one more thing down, since this fraction is squared, does it make sense the 2 on the bottom would be squared to become a 4, which means I could pull it out front. So it'd be a 4 out there with the 2 that's already there. That would be a good step to keep your brain from hurting too much. So I am not going to finish this because I want to spend all of our time today trying to conceptualize these. But to Eve's point, if you did square this out, the first one squared would make that go away. Then you multiply these together and double it.
Yeah, that's a lot more ugly than I was thinking it was going to be.
Yeah, so this is really the only thing that's ugly. And you would have to, and as I said, we're not going to finish it, but you would have to let u be equal to 2y minus 2, which means du equals 2 dy. That's not too bad. So the square root makes it ugly, and it didn't go away in this case. So you could definitely do this, but this section is about, can you set up the integral? You need to, the taking of the integral I want to be easy. Let's just try to set up another one. Let's consider y equals, let's see, the square root of x. So I'm just making this up from scratch. So the square root of x does something like this, right? And so let's chop it off out here at 9. So that's x equals 9. And let's also chop it off at y equals 0. So now I've defined this shape. Now the fact that this is against the y-axis will make it, I'm sorry, against the x-axis will make it a lot easier. But see if you can set up the integral for the volume of semicircles again, because that seems so hard. And let's make them parallel to the y-axis. So there's our slice. There's our slices. And they're coming toward us. They're coming up. Just set up the integral. See if you can set the integral up. And again, I want to give you time to do it wrong before we talk about it. Don't take the integral, don't get the answer, just see what you, just see if you can set it up. I think you're going to have the most success with this if you say, oh, these are cylinders. Volume of a cylinder, pi r squared h. What's h? Notice height doesn't always be vertical. Like this thing is turned sideways. And so there's its height and there's its radius. So that'd be a full cylinder. So if you say, great, what we're doing is adding up a whole bunch of those. Right. We don't just have one, we have a whole bunch of them. And they're getting smaller and smaller and smaller as you move down. And in our case, they're semicircles, which I forgot last time, right? So the fact that they're semicircles means I actually have to divide this in two, right? Because ultimately what we're saying is this part is chopped away. So now I just have to replace that. Can you look back up at the figure and say, hey, I know what that height is. That's a little bit of X. My H is a little bit of X. How do I get my radius? What's my radius?
Would it be the square root of x over 2?
Yeah, your height right here, like that's your y value, if you will. That's kind of the y of your square root function. But because we want the radius, not the diameter, we got to cut it in half. So this r is the y value of the square root function divided by 2. So because this time it went, and this is the example I should have started with in a sense, it went all the way down to the x-axis. So let's see, I'm just replacing stuff. So I have a pi over 2, that's annoying, so I'll just take it out front. So then I really have y divided by 2, that's my radius, and it's squared times my height. So what you're going to have every single time is, because you're talking about volume and one direction goes in X and one direction goes in Y, you're always going to have this mixture of Y's and X's when you write this statement down, and then you just have to go convert it. So we know that Y is equal to the square root of X. So we're going to have to switch all of this into X's. So now that we know we're working with X's, now we go back and we look at that shape and say, for what X's does this exist? Well, since it went all the way from here to here, that's X staying between 9 and 0, isn't it? Isn't that X value working its way from 9 to 0? So what makes this a calculus problem is our cylinders, the radius is changing all the time. As we move from 9 to x is 0, the radiuses are getting smaller and smaller and smaller and smaller. Okay, I think I have everything I need. Now watch what I do here to make my life a little easier. I'm going to square this out first to get y squared over 4, and then that 4 can come out front and be out there with the 2. Now it's over 8. Just much easier to work with. So this problem came out really nice. Now I'm going to stick in y is the square root of x. And yes, it's still being squared. So I can say pi over 8, and I'll go ahead and write it out. The square root of x is being squared. I replaced y with the square root of x. I now know that I'm working with x's, and then I can go and say, oh yeah, x is from 9 to 0. So this is a really easy question. Like the calculus of this is not the hard part. Square root of x squared is just x. Oh, that's really easy then. So I have x squared divided by 2. And again, this is a good way to write this. The integral is now taken and needs to be evaluated at 9 and 3. But, oh yeah, there's a pi over 8 out front that I need to take care of at some point.
Isn't it 9 and 0?
9 and 0, not 9 and 3. Thank you. So 9 squared is 81 divided by 2, and 0 squared is 0. So I have 81 pi over 16. Which I don't think reduces because 81 is made of 3s and 16 is made of 2s. So I have the exact answer to this. That was a much better problem, or much easier problem as an introduction than the previous one was. Whew. So these questions are all, and as far as your assignment is concerned, these questions are all defining an area. You know, oftentimes, like it did in this problem, it took 3 equations to define that pink area. But then the question is, what are we doing to make that pink area turn into a volume? Are we sort of stacking squares in it in some way? Are we stacking semicircles in it to make it kind of like an airplane wing? My advice with this assignment would be to wade into it today if you can, only so that tomorrow you can ask me more pointed questions. So we have another day to work on this, and I'm just going to keep doing examples and help you try to visualize this. But just make sure you're getting your questions answered. That's the thing that kind of concerns me. And I would particularly like those questions to happen in this environment where other people can benefit from them too. But what this has to do with is spatial awareness, like your ability to picture this, somewhat your ability to draw 3-dimensional shapes. Let's do one more example. Let's do something even kind of cooler that's related to the last problem. And that's making up my own language for this, but volume by spinning. This is much easier for me to draw. Let me show you what I mean. So let's consider, well, let's just consider the same equation, y equals the square root of x. But let's just think about that shape from x is, well, we're taking the square root, so I'd like this to be easy. So last time I went to 9. Let's go from 16 to 4. And let's spin that curve around the x-axis. Let's see if we can picture what I'm talking about there. So you got to be able to draw this out. So let's see, what are we talking about? We're talking about this from x is 4 to x is 16. And the square root graph looks something like this. And so how are we going to get a volume out of this? So we're only considering the part of this graph that exists from 4 to 16, really. We're only taking that part right there. And what are we going to do with it? Well, we're going to spin it around the x-axis. Can you picture what that's going to produce? Can you see that that is going to take the shape? And what I'm going to try to do is regraph this point down here and regraph this point down here. Can you see that it's going to create this volume? Do you see it? Do you see the shape that we're talking about now? So it's kind of like a cone, sort of, in quotes. If I was to turn it sideways, like a cone looks like this, except for what's different about what we have in a cone. What's different?
The
Well,
bottom is cut out.
yeah, the top's cut off, so that's gone. What else is different? The sides.
Well, it's more
It's
rounded.
round.
Yeah, it's like round. You see what I'm saying? So again, this is really cool. Like we have a formula. There's an algebra formula for the volume of a cone. There's even an algebra formula for the volume of a cone chopped off, a truncated cone it's called. But we're talking about the sides being curved. And so this is very different. But it's a really natural shape. I mean, it looks a little bit like a chunk of a bullet or something like that. There are shapes like this, and we'll look at that some more tomorrow. In my mind, this is the more important application of this section. You're not filling it with some arbitrary squares and so forth. You're spinning it to create a shape. Do you see the slices, which I'm going to draw now? Do you see that slice as a cylinder, like a complete cylinder? The slices are cylinders. And so I just have to add up those cylinders. So as before, I have a radius of that cylinder, and I've got the height of that cylinder. And in our case, I'm saying, well, then add them all up. Do you see that as the foundational equation? And again, why am I adding them all up? Well, because our cylinders are changing. They're big radius cylinders when they're down here, but they're actually fairly small radius cylinders when they're up here.
So would it be better to take this with respect to the X or the Y axis, in your opinion?
Yeah. So in a sense, we don't know the answer to that yet. Let me show you kind of how every problem develops though. Every problem kind of ends up developing like this. This little H right here, would you agree because that's horizontal, that's a little bit of X? That's what H is, a little bit of X.
Yeah.
And like last time, this R value right here, which doesn't look like an R now that I look back at it. What's that R value?
4.
It's 4, no, it's not 4. Where is it? Remember, this shape has to slide all the way through.
Yeah, it's the square root of X over 2 still, isn't it?
Does it make sense those R's are changing heights all the time? That those R's are basically the Y values of our square root equation, like last time?
Yeah.
So those R's are really the Y value. So then I'm just going to replace those. Okay, fine. Square root of pi times not R squared, but Y squared, and not H, but dx. Now, again, the way I think about this that I think makes it easy is what I've been saying before is we're stuck with X. We've got to work with X's, which means we need that Y to go away. Well, don't we know, just like last time, that Y was equal to the square root of X? And if I want to, I can pull the pi out front. And so Y is replaced with the square root of X, just like last time. And now that I know I'm completely working with X's, our graph lived between the X's of 4 and 16 in this case. So it didn't go all the way to a point. It was truncated. No problem that it's truncated. It went all the way to a point. So it's out from 16 to 4. X is 16 to X is 4. There, I've got my integral set up. And this particular integral is really easy to take. So let's do it really fast. So the pi came out front. We're from 16 to 4. The square root of X squared is X. So that makes this really easy. So I've got pi. I take the integral of X and I get X squared over 2. The integral has been taken, so the integral sign is gone. And now I evaluate that at 16 and 4. 16 squared divided by 2. What is that? It's just kind of nice to have the right answer. So 16 divided by 16 squared divided by 2 is 128. 4 squared is 16 divided by 2 is 8. So we have 128 minus 8, that's 120. So we get 120 pi. Again, it's crazy that we can say we have an exact answer for this cool volume that I drew in this picture right here, this curved sided truncated cone, conish type shape, has an exact volume. Again, I want this to ruin your life in the sense that you start looking outside now and you see shapes like this and you realize, yeah, calculus allows me not just to find crazy areas, but it even allows me to find crazy volumes. And what we're really talking about here, the biggest application that will continue tomorrow is that shape right there has got rotational symmetry. It's made by rotating something. If you're a person that's, I don't know, ever seen a machine shop, a lot of things are made on lathes, like metal. They'll put it on a lathe and turn it, and then they run a tool into it. Baseball bats, are made in this same fashion, but something that's made by turning it on a lathe. All kinds of shapes. So be thinking about that, like be looking around in this room that I'm sitting in right now. There's a light that I see over there that I'll erase this, but it kind of looks like this. It's got a rounded top up here. And then it's got this base that kind of sticks out like this. And so the light bulb is inside there. And so that shape is got rotational symmetry to it. So you see this kind of stuff kind of everywhere. So those things are made by turning something on a lathe, but they're also made by casting it and so forth. So my advice, as I said, would be to wade into this assignment. See how far you can get with it. Don't use all 3 of your tries. I'd love to start tomorrow by, instead of just doing some more examples, which we need to do, by you saying, here's what I did for question 7, and then I'll write down what you did, and then we'll talk about it for everybody's benefit, and why didn't this work, and then we can look at what you conceptualized wrong. I think there's like 14 questions in your assignment, and the first 3 or 4 are these sort of contrived questions where you take an area and fill it with squares or something. But the lion's share of these problems, like the other 11, or like this question that we just finished with, where you take the shape and spin it around. And so we'll talk about that entirely tomorrow. So stay after, get yourself out of here. I'm going to drive back to Oregon and be back at my desk in the morning.
Hey, Doug, I have a quick question for you.